Bonjour tout le monde. So I will not talk about collisional excitation today. This talk is about the mouse is working here. About the astrochemistry of nuclear spin isomers. And so this is a topic that we started to work on about 10 years ago in Grenoble at IPAG with Pierre-Élie Blanc and Roman Le Gall, and now also with our new PhD student Matteo Gaillard. And so I will not make a review of what was done in this topic in the last years. I will try to show you that our understanding of what we also call nuclear spin orthoparachemistry or nuclear spin chemistry have greatly improved in the last years, and especially thanks to laboratory work. So I will start with a simple case, a water molecule. So as you probably know, this molecule consists of two forms, the ortho para, which is 75% at room temperature, and the para water, which is 25%. And these two numbers here just reflect the degeneracy of the nuclear spin, which is 1 for ortho, and also the right of the screen is missing, and 0 for para. And if your water molecule is thermalized by any process, and if the temperature is decreased below 50 K, just like in this church, the ortho to para ratio will decrease towards 0. So the ortho to para ratio would be much lower than 1 below 20 K. And that this curve, which we call the thermal ortho to para ratio, is simply the ratio of the partition function of ortho and water. And now, because the gas phase nuclear spin interconversion is extremely slow, in fact, it's almost forbidden, you can assume that the ortho to para ratio that you measure in the gas phase for water has preserved the value at its formation. And so the general idea in the astronomical literature for long was that if you measure an ortho to para ratio of 3, that should reflect a gas phase formation, because you have a lot of exothermicity in gas phase reaction. But if you measure an ortho to para ratio below 3, this corresponds to low temperature, and so this was attributed to formation in the ice on dust in the cold ISM. And so this idea was largely employed by astronomers working on comets, and they started in the 80s with the first determination of this ortho-para ratio of water by Mike Muma and co-workers. And this is a recent compilation. So this is the ortho-to-para ratio of water. I'm sorry, the left and right side of the slide is missing. I should have checked this more carefully. But all these data points here are for different comets, about 20 comets. And you see that on average, the ortho to para ratio is 2.5. Believe me, it's here. And the spin temperature is about 30 K. And this 30 K was attributed to the temperature in the solar system at the epoch of the formation of comets. The problem is that there have been no laboratory evidence for these results, that the ortho para ratio is conserved, and that you keep a memory of the formation temperature. But fortunately, recently, this problem has attracted the interest of experimentalists. So in France, with our colleagues from Monaris, and also in Japan. And I will present this result by the group of Naoki Watanabe in Japan. So in this group, they made a series of experiments on water, where they formed water in the ice, they deposited water in the ice, they deposited water in matrices, and probably the best evidence of the result is from this last work, 2018, where they produce a pure para water film at 11 K, and they desorb the molecule by photodesorption and by thermal desorption. And in every study they made, they always measured the statistical ortho to para ratio of 3, which contradicts the idea of comets that this value could be lower than 3 and could reflect something from the formation of water. And so from these studies, we can conclude that a low ortho para ratio of water doesn't reflect the formation of water. And so even if the underlying mechanisms are poorly known, as would confirm, I think, my colleagues from Monaris, these results had a large impact, and it was even suggested that maybe these low values are not real and that there are some observational bias or in the radiative transfer, etc. And it's true that if you look at the most recent measurements, they go closer and closer to 3. So they are more and more consistent with 3, especially you can look at this, I think the very last measurement in Comet Churyumov, Gerasim and co, it's consistent with 3. But there are still exceptions. Comet Lovejoy, the value is the accuracy of the value you see is very good, and it's 2.5. But okay, there could be something special in water in comets. But the point is that these anomalous, I mean here non-statistical orthopolar ratio, are actually observed in other molecules and in a variety of environments. So you have here ammonia, water again, and formaldehyde, from comets to star-forming regions, photon-dominated regions, dark cores, and even in protoplanetary disk. And in all these environments, you see that most of the data points do not agree with the statistical value and points to low spin temperature. And in fact, we were motivated on this topic by these particular measurements here that I added on the ammonia plot. And we were asked, I think it was in 2011, by Marie-Yvonne Gérin to look at this and to try to understand this value, which is absolutely not thermodynamic because it's below the thermodynamic curve. So it was completely not understood at that time. And if we cannot explain these values with ice chemistry, then the only alternative is gas phase reaction. And if you remember, I said that gas phase reaction should result in statistical orthopolar ratio. But in fact, and so we discovered this, there was a theoretical work, an old one, 50 years ago almost, by Martin Kwak, about the impact of the conservation of the nuclear spin in gas phase chemical reaction. And this work was basically overlooked in the astronomical literature with maybe one exception. And in this work, Martin Kwak shows that if the total nuclear spin is conserved in a chemical reaction, then this will result in selection rules, nuclear spin selection rules. And if you assume that there is a full scrambling of the nuclei in a long-lived complex, so typically in an ion molecule reaction, then you can predict branching ratios. Not quite easily, but this is doable, and this is what we did. And so I give an example here for the reaction between OH plus and H2, the para form and the ortho form. This reaction goes through a long-lived complex, 3O plus, and the product is H2O plus, which can be produced in the para or ortho form. And as you can see, the branching ratios are different according that you react with para or with ortho H2. And so the ortho-para ratio of H2O plus will depend on the ortho-para ratio of H2. And so at that time, in 1977, there was absolutely no experimental evidence for this, for the conservation of the nuclear spin. And there have been only a few such measurements. And to my knowledge, the best evidence for the conservation of spin experimentally is certainly this work. So the year is 2021. It was published in Nature Chemistry by the group from Kankwen from Harvard. And so they were able to measure the reaction between two potassium rubidium molecules, which has absolutely no interstellar interest. But they were actually able to select these molecules in one single hyperfine state. And this reaction goes through, again, a long-lived complex, which is two potassium rubidium molecules. You have a full scrambling of the nuclei, and the products are two homonuclear molecules. And they were able to probe the rotational states of this and the even odd parity preference that you expect from the conservation of the spin was observed. So it's a best evidence, I think, for the conservation of the spin. And so we have implemented this in a chemical network that is called UGAN for University of Grenoble-Alpes network. So it is fully described in this network in this paper, sorry, from 2018. So it's a small network compared to famous networks like TIDA or UMIST, but we do include all the spin isomers of hydrides, including carbon, oxygen, nitrogen, sulfur. And recently, we also implemented the chemistry of formaldehyde, and I will show two results in the next slide. We employed it so far to study the orthopara ratio of water, ammonia, and deuterated ammonia. But here I illustrate what we obtained for H2, because H2 is a major player here, as I showed for hydrides, which are usually formed by a series of hydrogen abstraction with H2. This is H2 which drives the orthotopara ratios. And so H2 in the interstellar medium is formed on dust with a statistical ratio of the orthotopara ratio. That's what we, at least that we have in our network. And as you can see, at low temperature, the orthotopara ratio of H2 is actually thermalized. And this is because H2 collides with a number of ions, protons, H3+, HCO+, etc. And this collision drives the orthotopara ratio to the kinetic temperature down to about 20-25 K, where you see a deviation. Our results are here. The orthotopara ratio is flattens and reach a plateau at about 10 to the minus 3, which is 4 orders of magnitude larger than the thermal orthotopara ratio. And this deviation here simply reflects the fact that the conversion from para to ortho has 170 Kelvin of barrier, just because the ground state para is the ground state ortho state is 170 K above the para ground state para H2 level. And so in fact, there are two important results on this plot. The first is that in the cold ISM, you should dominate it by a lower orthotopara ratio, so by the para form of H2. And this is in agreement with observational evidences, for instance, of deuterated molecules, as was shown by Laurent Pagani in the room, for instance. And the other important result is that this value here, at very low temperatures, there is an amount of ortho H2 which is not negligible. 10 to the minus 3 is much larger than 10 to the minus 7. And ortho H2 is important for some reaction with slight endothermicity, just like for the deuterium chemistry. So this is important to know that you have a few ortho H2. So I will finish with an application to formaldehyde. So in our network, formaldehyde is formed in the gas phase. So we found that the dominant reaction is that one between CH3 and the oxygen atoms. To my knowledge, there is one single measurement at room temperature, and we've employed this constant rates at this value. And this is what we predict. So a value between 2 and 2.5 typically, so lower than the statistical value. And in good agreement with these old measurements by Dickens and Irvine in star-forming cores that were attributed at that time to formation in ice. But actually, we show that gas phase reaction can explain this low orthotopara ratio. And again, we expected a low orthotopara ratio because if you are dominated by para H2, you will favor the para form of any molecule. This is another illustration for the, this is a preliminary work by our PhD student Matteo Gaia for the protoplanetary disk surrounding the Titori star TW Hydra. That's ALMA observations that were able to resolve spatially the emission of formaldehyde and therefore the orthotopara ratio. And you see that we are also a good agreement, especially in the outer radius where the orthotopara ratio is close to 2. Which suggests a gas phase formation for this molecule. And so the two take-home messages are the following. So first, the orthotopara ratio do not probe a formation temperature. I think it's rather clear, at least from experiments that were performed so far. And on the other hand, anomalous non-statistical orthotopara ratio can be explained by gas phase chemistry if you include the proper selection rules. And as perspective, so we have started to explore the possibility of thermalization processes just like this one. So this was published in a work by Roman in 2016 for the collision between NH2 and H that can thermalize NH2 at the kinetic temperature. And yesterday I was told by Perpetua and Icharo that there is something probably similar for the complex organic molecule CH2CN, which has an ortho to para ratio of 8, I think you told me. And that could be a similar thermalization processes in the gas phase. And another exciting perspective was inspired by this experiment that you've heard about yesterday in the talk by Jutta Toscano. So this is an experiment in Basel where they are able to separate the para and ortho isomer thanks to a deflector. And they were able to show that the reactivity of the two flavors of water is not the same. And so if spin isomers have different reactivity, of course, this will have an impact on the ortho-to-para ratio of the molecules. And so to conclude, I thank my colleagues and collaborators, and I thank you for your attention.